Everybody. I would like to explain to you just a short introduction about NMR, and if you understand these basics of NMR, then you can go to my videos of solving problems and so on. After that, you can practice on your own structures, and definitely you will love the NMR after that. So the aim of NMR is structure elucidation. So if you get a compound from natural resources or even with organic senses, you would like to know the structure. And the only way for identifying the structure in case of new compound is NMR. Of course, mass spectrometry could help, but the NMR is fatal. Additionally, of course, we use NMR for structure elucidation of non-compound and with the help of X-ray and mass spectrometry. X-ray, of course, is also used for structure determination of new compound, but the main is NMR. NMR, it can be divided into one-dimensional NMR, which means that I will have a chart of only proton NMR or a chart of carbon-13 NMR. That's why we call it 1D. If you combine, for example, proton with proton correlation, then it will be two-dimensional because you get relation between two. Proton, then it will be cozy in case of neighbored protons, toxy for long range until 3 bonds, noisy in order to determine the stereochemistry. Then it can be correlation between proton and the carbon, and this we call it HSQC, and you can have it as HSQC depth. And the H-carbon correlation, which we call it HMVC. In this lecture, we will focus only on 1D NMR. Here is the 3 main points we will discuss about delta, which means that the chemical shift. So this we call it a chart of NMR. When it is proton, then the chart is from 0 to 15. This we call it delta ppm. In case of carbon-13, it is much a bigger range, which is from 0 to 220. Then we call it carbon-13. Here we call it peak. And this peak, as you can see, it is only one line, so we call it singlet. This is 2 lines, but it's only one peak. It's called it doublet. This is 3 lines, triplet. This is 4 lines, quartet. So what is the difference between all of these? Also, you have to notice one thing. When it is doublet, it is almost with the same intensity 1 to 1. If it is triplet, it is like 1 to 2 to 1. Right hand and the left hand, almost the same intensity, also in quartet. Right and the left is the same, and the middle is almost double. But here, you can see the peak is broad. And when the peak is broad, immediately you call this functional group. So for proton NMR, the proton can be like CH3, CH2, CH, aliphatic, or it can be aromatic, like CH aromatic in benzene ring. What about this? The functional group like OH, SH, NH, NH2, all this is functional group, and you can see it like broad peak, so you can recognize it. If you would like to prove it, of course, you prepare the NMR in deuterated solvent, like for example, the chloroform. This is a normal chloroform, but when you prepare the NMR, it must be in deuterated, so you must use deuterium solvent. Deuterium means you substitute hydrogen by deuterium, or like in methanol, CH3OH. Then the deuterated solvent will be CD3OD. That's why the solvents for NMR is extremely expensive, because you use deuterated solvent. Additionally, the machine itself is very expensive, because as I told you, it is the only tool for structure elucidation of novel compounds. Moreover, for maintenance of NMR, we have to keep the level of nitrogen and helium, and this is cost money. So the running costs for NMR is very high. So, if you would like to prove the functional group, then suppose you have prepared the sample in methanol, deuterated. Then you would like to prove the functional group. then simply after you run the NMR, as I explained in my video in English, then you redo the sample again, but you add just 1 drop of D2O. If you add 1 drop of D2O and rerun the sample again, then the peak of functional group will be exchangeable or will be disappeared. This is the approval of the functional group. But the D2O doesn't influence CH3 or CH2 or CH, aliphatic or aromatic. Right, so this is the difference between the two peaks. What about carbon-13? It is usually in lines like that, and we will explain it in more details. So this is just an overview about NMR, then we go to details how we can interpret the proton NMR. I will discuss with you first about the chemical shift, which is delta. Why we need the chemical shift and why it is so important to explain and understand the chemical shift of the protons. Let us talk about aliphatic and aromatic compound. Right? So, in very easy way, if you see this is a scale of proton NMR, and it started from 0 until about 6, we call it aliphatic. So this you will see the aliphatic region, which is CH3, CH2, CH. And from about 6 until about 8.3, then you will see the aromatic. After that, you will see the functional group. Right? So, as you can see, the range of aliphatic is more, and aromatic just in a specific region, and the functional group we already know how to prove it. So, if we take we'll take you some examples, and we give you some examples. CH3, CH2, CH2, and CH3. And then, if we take CH3, the same exactly, but here you will have carbonyl group, and the rest is the same. And then we'll take CH3 attached to oxygen, and the rest is the same. And then we'll take CH3 attached to oxygen, attached to benzene ring. And if you take CH3 attached to fluoride, for example. Now I would like to explain to you the delta. And what is the factors affecting the chemical shift? If you see this methyl group, it doesn't affect by anything. You don't have any atom, like oxygen or nitrogen or sulfur. You don't have double bond. You don't have benzene ring. It means that the methyl group doesn't have any influence or any effect. In this case, it will be, you will find it around the 0.8. What about if you have carbonyl? The oxygen or nitrogen or sulfur, according to physical organic chemistry, it activates the structure. So it is higher in electronegativity. It starts to withdraw the electrons from here, and accordingly withdraw the electrons from here. So withdrawing of these electrons from methyl group, it means the electron density will be less. It means it will be de-shielded. So it will not appear at 0.8. It will be appeared around, in this case, it will be appeared around 2. So you see? What about if the oxygen directly attached to the methyl group? The inductive effect is distance effect. So the oxygen here withdraws the electrons because it is higher in electronegativity. That's why we call it inductive effect. So now the oxygen is directly attached to the methyl group. It means it is more a strong effect than this. It means it withdraws more electrons. Accordingly, the chemical shift will be the same or will be even higher. More de-shielded. I can hear you. It will be more de-shielded. That's why we'll see it around 3.3. Then again, the methyl group attached to oxygen, but then further attached to aromatic ring. Then you will find it around 3.6 to 3.9. What about if attached to fluoride? Will be see it around 4.2. All this means that you can see that the methyl group started from 8 and you can see it until 4.2. In the range of 6, it means that the inductive effect is a strong effect or little effect? Very strong effect. So the factors affecting the chemical shift now, the first factor we call it inductive effect. Inductive effect, or I, which means that withdrawing of electrons makes it less in electronegativity and it will be more de-shielded. Right. What about in case of aromatic ring, like benzene ring? You will see the benzene ring itself, it will be around, if these protons will be around 7.2. And you will see only one peak of the 6 protons. Why? Because all the protons are magnetically and chemically equivalent. All are the same. So we'll see one peak with the 6 protons. What about if you put here hydroxy group, for example, and here we say, when you put hydroxy group, now again, oxygen has electronegativity, then it will give the electrons in this case by resonance effect. So this is the second strong effect in case of resonance. So call it resonance effect or R. And R means that this oxygen will donate, in this case, donate the electrons. It means that the electron density will be increased or decreased? Will be increased because it is donation. That's why we call it electron donating group. Accordingly, it donates the electron to the position. This is also meta-para. So it gives the electrons more to ortho position and the para position. So instead of that, you see the protons in case of benzene ring, we will write benzene ring here. You will see all the protons at 7.2. In case of you add hydroxy group, you will see it at around 6.7. Why 6.7? Because now you give electrons. So it will be, the electron density here will be more. It means that it will be de-shielded or shielded? It will be shielded. So it will be increase the delta value. I think now it is more clear. Right? I will give another example. If you take another example, and instead of adding hydroxy group as electron donating group, it will be electron withdrawing group, like nitrobenzene. Right? And here is methyl group. So these are the same exactly. But the nitro group will withdraw the electrons from the benzene ring. Then what do you expect? The chemical shift of ortho position will be 7.2 or will be more de-shielded. You withdraw the electrons. It will take the electrons from the benzene ring. It means that the electron density will be less. This means it will be de-shielded. Accordingly, you will see that it will go to around 8.2. So I think now you agree with me that you will love the NMR because the rules of the physical organic chemistry, inductive effect and the resonance effect is inconsistent with what you see in the NMR, right? So these are the most strongest effect to the chemical shift. So, in another way, this is the reference, which is 7.2, and this is the factor which affecting the chemical shift. In this case, it is electron donating group. It means that you don't see it in the normal position, which is 7.2. You will see it in less delta value. It means shielded. And vice versa. Nitro group, it will be affect the benzene ring. So you don't see it at 7.2, which is the normal position. But you will see it in de-shielded, which means around 8.2. I hope it is more easier now. What about the other factors affecting the chemical shift? It is also temperature, but temperature is very little effect. We are talking about 0.2, 0.3 maximum, for example. So you cannot compare it with such a big effect, very much effect. Here also is much effect. Another factor, which is the solvent. If you run the sample in CdCl3 and you rerun the sample again in CD3OD, you will see very little difference. 0.1, 0.2, very little. Right? So it is less effect as well. Final factor affecting is hydrogen bonding, and I will give you an example about hydrogen bonding. So this is my students and people are interested of NMR are the summary of factors affecting the chemical shifts. Let us take examples and see how we can see these factors and how we can interpret the spectra. I will take this example, for example, as I told you, OH, and here is methyl group. How many proton we will see here? Right? How many type of proton? First is this proton, which is functional group, right? And now you know how to prove it. This broad band, broad peak, and you can add DTO. And this one proton, and one type of proton. So in total, 1, 2, 3, 4 peaks. This is a methyl group. Where you will see this methyl group? In aliphatic region, right? And you will see it at 0.8, or it is attached to benzene ring, then you will see it at higher delta value. I can hear you. It will be more deshielded. What about these two protons? How you will see these two protons? This is one proton, and this is one proton. Is these two protons are magnetically and chemically equivalent? So you see it only in one peak? No, because this is ortho, meta, and para. And this electron density, it goes here, and by resonance, it will increase the electron density in ortho and para. That's why we call it ortho-para directing group. So positive R means electron donating, and you call it ortho-para directing group. It means that it will be different. So when you see these two peaks, then how you will see it? We have a rule called the N+1 rule. And this rule means that this proton affected by which proton? This is a neighbored proton from this side, and here no proton. It means 1 + 1 = 2. So you will see this as a doublet, right? And as I told you, it will be around 6.8. But this proton, you will see it also again as a doublet. Then it will be doublet. But the chemical shift, it will be around 7.3. In this case, if these two protons are neighbored to each other, you will see that they are mirror to each other. So you will see it like that. You see? So if you see this feature, it's like that. Immediately, you will see that they are mirror. It means I have AB spectrum. It means I have a benzene ring, and this benzene ring has a para substitution. Why? Because this para substitution is the only way to get such a AB spectrum. This para substitution divides the molecule. So these two protons are exactly the same. These two protons are exactly the same. Right? And then I will go with you to why we can see the intensity of the peaks in such a way. You remember when we draw the first spectrum, we say that it is triplet and both sides are similar and the middle line was double. This followed by this very nice rule. It is Pascal rule, Pascal triangle, and this Pascal triangle showed you that this is the intensity of the peak. So when you have a spectrum, like what I have drawn before, And then you have this spectra, you would see the singlet like that. Then if you have doublet, you would see it like that. If you have triplet, you would see it like that. If you have quartet, you would see it like that. So why this doublet, this is a doublet, why the two lines are almost the same? And here, the first and the last approximately the same, while the middle is double. Again here, the right and the left almost the same, while the middle are double. This is controlled by what? By a very nice rule, which you can play with it, as I usually say to the student. So if you write here 1, this means 1 and 1. Then you can see it 1 to 1. This is intensity. Then the next, every time right hand side 1 and 1. What about in the middle? Is the summation of both. 1 plus 1 is 2. Then you will get this 1, 2, 1. This is the intensity. So this we call it peak, but it is singlet. This you call it peak, but it is doublet. And this is the intensity of doublet. This you say triplet, and this is the intensity 1, 2, 1. Here is quartet, and this quartet again on the right hand side 1, left hand side 1. In the middle 1 plus 2, 3. 2 plus 1, 3. That's why you can see the intensity 1, 3, 3, 1. Next, again 1 and 1. And here will be some 1 plus 3, 4. 3 plus 3, 6. 3 plus 1, 4, etc. I think you agree with me that you love the NMR. And this is the second factor, which we call it multiplicity. So the multiplicity, why you need it? I will give you an example. If you take this example, like for example, here is CH3, CH2, OH. Now, I would like to expect with me how you will see this spectrum. Take this group, then how you will see this group, I will follow the rule, N plus 1 rule. N means the neighbored hydrogen atom carried by carbon. So if you talk about this methyl group, how many proton here? They are 2. 2 plus 1 equals 3. It means that you will see this peak as a triplet. Why triplet? Because 2 plus 1 is 3. So if you see this triplet, like this one, immediately you say the neighbored group is CH2. So triplet is not expression of the methyl itself. It is expression of the neighbored group. So here, if you say that you see this as a triplet, it means that you say, right, isn't neighbored group is CH2. You got it? We can apply to this one here. This CH2, if we say N plus 1 rule, how many here is 3. Here, this is functional group, so you don't consider. You consider only the hydrogen carried by carbon. So 3 plus 1 equal 4. It means that this CH2, how you will see it? You will see it as a quartet. Quartet. What means a quartet? It means that the neighbored group must be methyl group. So in the final, you will see the structure as like that. You will see the spectra like that. Triplet, quartet, and the broad peak. Immediately, now I can hear you. Immediately we say the broad peak is OH. Finished. Then, again, I would like to explain this. Immediately when you say triplet and the quartet, if you see triplet, then immediately write CH2 group. You must have neighbored CH2. If you see quartet, immediately write CH3 group. Now you can see that, you know that. Why? Triplet and the quartet, it must be ethyl group. No other way. Triplet, quartet means you have ethyl group. So the multiplicity, is it important or not? It is very important. Why? Because it gives you an idea about the neighbored group. So if I know that the neighbored is CH2, I write CH2. If I know the CH3, then I write, so I could write the part of the structure. So this is the second, which I would like to explain. Additionally, what is the coupling constant? I will give you an example. Coupling constant help you to know if the protons are neighbor and they are cis or trans. What means cis? What means trans? I will give you an example. Like in benzene ring, when we take this example about NH2 this time, and this proton both are cis. It means that when you see the doublet, you will see the doublet like that. Right? Or when it is AB spectrum, as I told you before, the AB spectrum, this will be doublet, this will be doublet. So the AB spectrum, you will see it like that, and the other one is mirror to it. So here is the coupling constant. So this coupling constant will be around 7, because the two protons are cis. Right? What about if you have another example, like this, for example, and you have these two protons, they are neighbored again to each other, but in this case, the two protons are trans to each other. How you will see the peaks? You will see it this way? No, you will see the doublet like that. You see? The distance between the two lines in the doublet is almost double. It is around 16. So it means the multiplicity and the coupling constant, we call it J, and it is in italic, it is very helpful. Because immediately when you see the two lines are far away and the coupling constant, which calculated now by machines automatically, it will help you to identify if they are cis, it means in the same direction, or if they are trans, which means they are in opposite direction. This is the second point which I explained to you. Additionally, one more thing, sometimes you see the coupling constant is very small, which is around 1 to 2. It means, oh, the two protons are too far from each other. Like in case of flavonoid, for example, if you have this system, this is usually you find in natural products, the flavonoid. And here is one proton, and this is one proton. They are far away from each other. So if you apply the rule, n+1 rule, it means that 0 + 1 = 1. But when you see it like doublet. But you see the doublet like that. The two lines are very close to each other. Why? Because the coupling constant is about 1 to 2. So immediately if you see the coupling constant is very little, is very small, 1 to 2, it means that you have meta coupling. They are not close to each other. They are not neighbored. They are separated by carbon. That's why we call it meta coupling. You will see this a lot in NMR. So I hope is clear for you now about the 3 cases of the coupling constants. What about the last point here, which is about integration? As we have seen in the last example about the alcohol, we have seen the alcohol is like this, right? The last spectrum about ethanol. So it was CH3, CH2, OH, right? So this is CH3, CH2 and OH. Then you will see the integration like that. This is. So means that you have 3 proton, 2 proton, 1 proton. So the last factor we are talking it's about integration, and this is very easy to understand because if you look to this methyl group, you will see that the line which overlapped with the peak is the expression of the number of hydrogen at the same group. So you see, this is the difference of integration than multiplicity. And with the new machines, you will see the number written here. So it is like 3. And here you will see the integration is less, about 2/3. Then you will see it is 2. And here the integration is only 1 proton, so you will see 1. So now you know how to calculate the hydrogen of the same group, right? Try to practice here. This is triplet and this is quartet. So triplet and quartet. Triplet means that you have neighbored SH2. Quartet means that you have the neighbored SCH3. Then you have CH3, CH2X. And since you will have this prod B, it means that you have a functional group. So you write here functional group. Now we finished all the factors of the proton NMR. It will be easy for you to understand the carbon 13. Why? Because factors affecting the chemical shift of the proton are the same exactly factors affecting the chemical shift of the carbon atoms. To make it easier for you, then you will see that the range, which is from 0 till 220, I can say to you that until 100 it is the CH aliphatic, which it can be like CH3, CH2, CH, right? So why it is very big range? Because range is 220. And you can see the methyl group at 10, but you can see the methyl group at also 50. Why? Because of the same factors which we discussed before. If no effect at all, it will be at 10. If you put oxygen atom, then it will be deshielded. So I will not disturb you with more interpretation. So then, after 100, or from about 90 even, until about 165, then you will see the aromatic, CH double bond CH, and also and also triple bond CH, triple bond C, also you have C triple bond N. So all this you see it in this region, right? From about 165 until 220, you will see the carbonyl group. And this is spectacular here. It is little overlap here from, we can say, 162, but after 170, you never see the aromatic proton. So this is very spectacular, only 2 carbonyl group, the functional group, which is carbonyl. Remember, you cannot see carbonyl in the proton NMR, but you see it only in the carbon 13, except of course if it is in the aldehydic form or in carboxylic form, which means that if it carry hydrogen atom. Moreover, so now we discussed delta. Regarding the multiplicity, you usually don't make it in the carbon 13. Sometimes you can do, of course, using the machine, but it will be expression of the protons carried by the carbon itself, by the group itself. Then the integration also you don't see or you don't calculate. So this is very short idea about the carbon 13. Of course, remember, if the molecule contains 20 carbon, it means that you will see 20 lines, 20 peaks, right? Unless, of course, if they have 2 carbons are similar, since the same rules of proton. The similar carbon atom, magnetically and chemically, are equivalent, you will see only 1 peak, right? Usually also in the intensity, you will see that the CH3, it has higher intensity than CH2, than CH, than if it is only carbon. This is usually. When it is more hydrogen, of course, the intensity is more. So this is the carbon 13. There is another technique of the carbon 13 which is very useful in the interpretation, and we call it depth. And the depth means that distortion, enhancement, polarization, transfer. So this depth classified user carbon, then it will help you for structure elucidation. So this is, you call it depth, DEPT, which is distortion, enhancement, polarization, transfer. And this depth, you will get first the carbon 13 of the whole structure. It means that you will get the carbon, all carbon in the structure. If you have terpenoids have 30 carbon. And if the 30 carbon are magnetically and chemically different, it means that you will see 30 peaks. So in the first carbon 13, you will see the 30 peaks, right? But what about depth? You will see another line. And in this another line, you will see some peaks up. And some peaks are down. So what is up and what is down? The up will be the odd number, CH3 and CH. And the down will be the even number, CH2 and the carbon. So this classification definitely will help you in structure elucidation, because you will differentiate between how many methyl and CH are up and how many CH2 and the carbon are down. This is, you call it depth. Of course, when we come to two-dimensional NMR, you will interpretate HSQC depth. This we will HSQC depth. This you will help us more in structure elucidation, and I'm going to discuss with you in the next lecture about two-dimensional NMR. Remember also in the final that you can go to solve the problems in the other videos, and then practice with your structures. Then you will love the NMR, and you will be definitely better than me, as I usually say, because you take all my experience, but you are more younger and you have a better facilities than I was in your age, and therefore you will be for sure better than me. All the best of luck. Thank you. Hisham, LCET.